Hello, good morning, good afternoon. I don't know the time you're going to get to have this video with you. Allow me to introduce myself. Mr. Mlenga here. Today, I want us to look at modes of, okay, let me just talk about analytical stuff. Yeah, let me take it that way. We understand very well that in analytical industry, we are involved in the analysis, let me say, starting with the collection of data. You collected data from different samples. That data may be in form of, maybe in gaseous state. That data may be in liquid state. That data may also be in solid state. Now, I think today's discussion will base much on the solid samples. Yeah, will base much on the solid samples. Now, we understand very well that among the solid samples that one might think of, there may be rocks. Yeah, let me say there is an assumption, or maybe an allegation, maybe just a tip which has come through that among that rock over there, there is a very, very precious a very precious mineral that is present therein. So it's a duty of an analyst to make sure that he or she goes there to collect the sample. And now you don't get the whole lot of the rock and then say, I'm going to test everything in there. Of course, there are methods of sampling that we follow, depending again on the physical state. Is it a gas, is it a solid, and stuff like that. Yeah. Check some of the previous videos that I've done. We're talking about stages that are involved in sampling. First of all, you need to have a desktop stage where you just look for the methods that will be used in sample collection, things more or less like just planning. Yeah, you're planning on how to do the sample collection. And then when you're done the desktop stage, then you go to the implementation stage, where you put everything you had planned into now a good use. Let's say now you want to go and collect the sample. You need to know how many people will be there to collect the sample, the right equipment. You also need to know the people now that will be involved in the actual analysis during that implementation stage. That's when the issue of specialization comes in. Yeah. During the design stage, anyone is free to participate, anyone is free to contribute. But during the implementation stage, that's where you need to have now the right people to do the right job. So now once you collect that sample, before it is ready for analysis, how do you make it ready for analysis? Because some of these analytical methods that we use, or analytical instruments that we use for analysis, they do not allow the input of a lot of samples. Some of them, like HPLC, high performance liquid chromatography, you use a very, very small amount of sample to be injected into the machine. Now, in an environment or in a situation whereby you collected solid samples, so it is important that you have to convert it into a usable state. And with all that said, that's where this issue comes in. How do we crush the stones? How do we get the solid samples, convert them into the usable forms? So that is where our discussion will be based today. So today we'll be looking at methods. I think it's just one method that we can use to get the solid sample and then put it into a usable form. Now, in as much as we know, we may have, let me just clear this part here. Okay, you may have the sample, this solid sample here. Solid sample is very huge, yeah? This solid sample is huge. Now, how do you collect that solid sample? So when you collect that solid sample, you need to crush it. You need to reduce the size. Reduce the size of the sample. Now, the method of reducing the sample, that is of great importance in our today's discussion. In simple or secondary school laboratories, some samples that we deal with are very soluble even in water. Let's say you want to analyze you want to analyze the nutritional content of powdered cassava. What do? Just get that cassava, soak it in water, so to make a liquid sample. But now some of these rocks that we work on in the industry, let's say copper, you can't just get copper and dissolve it in water. I know I'm trying to prepare an aliquot. It's not possible. So different methods, of course, are likely to be applied. So today we'll be looking at what we call ashing method. Ashing method, there are two types of ashing method. There's what we call dry ashing as well as wet ashing. Yeah, the two types of ashing methods is dry ashing as well as wet ashing. Today's discussion is entirely coming from wet ashing. So wet ashing is likened unto microwave sample digestion, because microwave sample digestion, we're talking about more or less like decomposing the rocks. Yeah, we're talking about exposing these rock samples into high temperature, but in the presence of an acid. That's why it is called wet ashing. Wet ashing, it is because a solvent is present during the exposing of these solid samples into high temperature in the presence of the acid. So what is the microwave acid digestion? And by the way, among the methods that we use to analyze these common ions or metal ions, there's what we call AAS. Is what we call AAS. AAS is called atomic absorption spectroscopy. There are quite a lot of the spectroscopic methods that we use for analysis of metal ions, and one of which is this one called AAS, atomic absorption spectroscopy. Then the other one is called AES, it's called atomic emission spectroscopy. Very soon, not too far from today, I'll be making videos on how to go about AAS, what is this, and how is it used, and then also have a look at AES, and then from there we'll go to Beer-Lambert law and stuff like that, so that we lay the foundation on where to stand when you're looking at atomic spectroscopy. Okay, so we're saying that to perform atomic absorption spectroscopy or atomic emission spectroscopy, the sample must be dissolved before the analysis. That's the same thing that I say no matter how big the sample is, for as long as you want to be subject to analysis, you have to make sure that you reduce in size. Not only in size, you also have to make sure that you dissolve it so that it becomes a solid, a liquid sample. Yeah, that's what I say. Of course, there are some methods like other different types of chromatography. You can analyze even you can analyze even the gas, the sample is in the gaseous state. But to do with atomic absorption spectroscopy, as well as the emission, atomic emission spectroscopic methods, you have to make sure that the sample is dissolved. Now, before you dissolve that sample, some samples are not easy to dissolve in water. That's why dissolving them, you might use an acid. Of course, some metals may dissolve in acids at room temperature. Other metals may not dissolve in acids at room temperature unless you increase the temperature. Unless you increase the temperature. So I think that microwave acid digestion is a form of, microwave digestion is a form of acid digestion, which is wet ashing. Yeah, that's what. Now we're saying that due to the advancement of technology, there are a lot of machineries that have been derived or that have been advanced from the late 1980s when technology was just coming up. Many more methods have been made, advanced ones and stuff like that. So we're saying that in microwave, I'm just focusing on those points that are highlighted. We're saying in microwave digestion, samples are usually placed in an acid and then at a very high temperature pressure. I think I talked about that. So some liquids, some metals may dissolve in acids that are at room temperature, and others can only dissolve faster, can only dissolve at all when the acid is heated. Of course, even those that can dissolve in cold acids or acids that are at room temperature, to speed up the process, it's always important that you increase the temperature. That is what this point is trying to emphasize. Now, the other point here says that these extreme conditions, what conditions? High temperature and high pressure, as well as the presence of an acid. These extreme conditions dissolve most of the metals. Like I said, even those that cannot dissolve in cold acids, when you subject them to high temperature, you subject them to high pressure, you find that they tend to dissolve. So we're saying that now, when you see, when you're dissolving these, because we are talking about in the presence of an acid, and remember, acids at a very high temperature, we are likely to experience the production of hydrogen. And you see, some of the people that work in labs, they have asthmatic conditions. So now it is important to make sure that even as you use these microwave acid digestions, but even as you design as implementers, it is important you take into consideration the fumes. For as long as there's a liquid boiling, you expect to have that vapor coming out of it. So now how do you maintain that? Yeah, so it is always important to do that. And then not on that, you find that if you are boiling, let me say, water, which contains salt, as the amount of water reduces, you find that you're likely to experience some jumping off of some salts jumping off the heating vessel. Yeah, so it's important also that to put all those things into consideration to avoid or to minimize the loss of the sample. So we're saying that these extreme conditions will dissolve most metals, but it is potentially quite dangerous, exactly like I'd said. It's a little bit dangerous because of those things that I've just itemized. Okay, so the microwave oven has safety features. So it's important that you understand these safety features, even as you work in the lab. Okay, all of which must be paid attention to when in use, exactly. The container are fabricated of high temperature polymers. So it's important that for as long as the heat is involved, you make sure that the walls of this microwave acid digestion machine, the walls must be resistant to high temperature, even resistant to acid corrosion. Yeah, they're saying because of that, it is likely to contain some with less likely to contain the metals. Yeah, because metals, you see, metals and the acids and all that, metals might dissolve. So make sure that the walls are made in such a way that temperature should not be the factor, as well as the presence of hungry and angry hydrogen ions present in the acid. So we're saying that the sealed depressurized containers reduce evaporation. evaporation. Exactly the point that I mentioned. For as long as there's a liquid boiling somewhere, we expect to have the vapor. So to make sure that the vapor, which might also help in the metal that you want to dissolve, to escape, and by so doing, you are reducing the content of the of what remains inside of the machine. By so doing, again, you are lowering the percentage yield. And you know, each and every time we're in the lab, we work towards the perfect results. Now, if you employ someone, this person does acid digestion, has spilled a lot of chemicals on the floor. As a result, whatever remains, you put it in the machine, you analyze, you're able to deceive yourself to say, I think the content of chromium in this sample was not that much. When the guy was doing the acid digestion, I just lost it. So it's important that we minimize the evaporation. Yeah, so I'm saying the seed container also eliminate the losses of more volatile metal species. So there may be some metals that are very volatile, and by so doing, you find that when you are doing this, you find that maybe part of it goes. So to prevent that, you need to do much of the sealing. So saying that can be a problem in open container sample decomposition, especially in dry ashing. You see, I've spoken of dry ashing and wet ashing. So I'm saying in dry ashing, you don't use an acid. You're just getting the sample and then expose it to high temperature. Now, because there is just high temperature there isn't much overboiling. As a result, you find that they do not seal the container. The container may be left open. It's just a decomposition. And they're saying that in dry ashing, you find that a lot of samples may be lost as the process of decomposition is going on. So we are saying that finally, we need to control the fumes. Yeah, the fumes of the acids, which I had even talked about. So it may be important that even the fume that comes out of this machine has to be worked on, because this is most of the times they use nitric acid, hydrochloric acid in the presence of hydrogen peroxide. So that fume that comes out is acidic in nature, you see. And once that is allowed to accumulate in maybe in the upper areas of the laboratory, some things might be corroded. So to prevent that, you make sure that that fume is neutralized before it is let go into the environment. So do not forget, we are talking about acid digestion. Now, why do we need to go for acid digestion? Why can't we just do dry ashing? Yeah, why can't we just hit these metals and then we just maybe crush them? Yeah, because you know, hydrated copper sulfate is blue in color because of the presence of waters of crystallization in there. But now, when that copper sulfate is heated, that hydrated copper sulfate is heated, it changes the color to black. You see, so it helps us to have a reminder, to get a reminder that these metals, even copper, is likely to decompose, maybe that way. But why do we recommend that before the sample is taken into atomic absorption spectroscopy or atomic emission spectroscopy, the sample must go to acid digestion? So these are some of the benefits. These are some of the reasons why we need to go for that. So one of the things that there's cleanliness in the preparation of the sample. Yeah. Because the machine has to be designed in such a way that if there are dirty stuff, if there's dirty in there, it comes out of the smoke. It comes out of within the fume. You see, so there's quite a lot that is involved there. It's very clean, very clean. Then the other one is that it produces the digestion is reproducible. Reproducibility is a term. Reproducibility is a term that talks about the fact that when two people are carrying out investigations on one sample, they should be able to produce the same results over and over, reproducibility. So now, once this acid digestion is performed on the sample, you find that there is quality control and quality assurance that is improved. We are likely to improve the assurance of the working environment. Here, you are likely to provide an improvement in terms of quality control, in terms of quality assurance. QA represents a quality assurance, then QC represents quality control. Then the other one is that it reduces the skill level as a factor. What does it mean? You see, in these other non-automatic processes, you find that for you to do that duty, you need the skill. Well, we're saying that here, the machine does the work, just load it, set the temperature and the conditions, and then everything is done by the machine. So it reduces the skill level as a factor. Then the other one is that it's very fast. If you needed to dissolve this metal in an acid, which is very cold, and then when you hit the temperature, when you increase the temperature, you also increase the pressure, you find that the time it's going to take is going to be reduced. So that's saying that greatly reduces the preparation time. So these are some of the benefits why one might give a recommendation of going for microwave acid digestion. The other point here that we need to emphasize is that it may also provide monitoring and recording of both the temperature and the pressure in the container. Yeah, but for dry ashing or decomposition, it's really difficult to tell the temperature at which the samples are being decomposed. But in here, you are able to provide that constant monitoring in terms of the pressure as well as the temperature. So saying that the sample containers are relatively high pressure containers, usually made of very strong high temperature resistance polymers, and of course stuff like that, as well as being resistant to chemicals. It's something that I had mentioned even earlier. So now we're trying to get the modernization, saying that modern microwave digestion systems monitor both the pressure as well as the temperature in the containers. That's something that I've even talked about. So meaning you are able to set the temperature at which the machine should be performing the work. You need to set the temperature. You also need to set the pressure. That's why we're saying that in this acid digestion, there's constant monitoring of temperature, there is constant monitoring of the pressure. And then the other point is that both the digestion time as well as the power can be programmed when you are working on the sample. It's quite advanced because you are able to set the temperature. That's why among the benefits, we say that there is a reduction in terms of skill as a factor. Yeah, it's a machine. You can just give instruction to someone. Okay, when you go to the machine, set the temperature at this figure, the pressure at this figure, and then load the sample, the machine does the work. As soon as that temperature is reached, we find that there's an automized way of doing things. The machine goes off to prevent the over-digestion of the sample. So even in as much as we know that technology has brought some harm, of course, there are some advantages that have been attached to the improvement in terms of the technology. Certain things, certain duties that might back in the days would need maybe 7 people. This time around, just need 1 machine and an instructor, and the work is likely to be done even in the better way as compared to the one that is done by the people. Okay, now let's look at this point here, how the thing is done and what acid is used, the conditions and things like that. So saying, if you want to dissolve alumina samples, you want to dissolve the samples that contain aluminium, remember that aluminium is at times it behaves as if it is very unreactive. It's because it has got a protective layer. Yeah, so samples that have aluminium, we're saying that the boiling point, or rather the mixtures, or rather the samples that the acids that must be present in the acid digestion machine, you need the mixture of phosphoric acid as well as sulfuric acid, not nitric acid, but phosphoric acid as well as sulfuric acid, and the temperature is likely to be above 280 degrees centigrade. But I'm saying that similar samples can also digest. Now look at the comparisons that are here. They're saying that alumina samples in the presence of sulfuric acid and the phosphoric acid, the temperature has to be a little bit high, and the pressure PSI also a little bit high, 40 PSI, and the temperature 280 degrees centigrade. Now we're trying to make the comparison here. Same sample can digest at the temperature lower by 40 degrees when you use the nitric acid, except that the pressure is likely to be higher than the one where the acid being used is nitric, is phosphoric acid as well as sulfuric acid. Okay, so that's what we were talking about. Now I'm saying there's certain ovens, especially those old ones, they do not have a capacity to do temperature and sample monitoring. So if that is the machine that doesn't provide that constant monitoring of temperature and pressure, then it is important that we calibrate it. Yeah, the calibration is a phenomena which is performed on most of the machines to make sure that we improve quality control as well as quality assurance of the samples. Okay, okay, these are some of the modules that I used, or methods. That's this EPA 503020. Okay, they're saying that this one is used to analyze the matrices of the sample, segments, slag, oil, biological, and botanical materials. So if you want to work on those samples, you know the method to use, which is EPA 23052. Now, it is important that we understand the solvent. Yeah, it's important that we understand the reagent selection. Why? It is because some of these metals that we're talking about in here, they form complexes. Metals such as vanadium, metals such as chromium, iron, and magnesium, these metals form complexes. So you find that metals that form complexes, they are vulnerable to acids that are able to contribute the ligands. The metals that are likely to form complexes, when you're choosing the reagent, it is important that you avoid acids that are able to contribute ligands. Could be a monodentate, could be a bidentate. It doesn't really matter the amount of coordination that this ligand brings to the central metal, but it's important that you have a better choice of the reagents. Here they're saying that typically about 9 milliliters of nitric acid are placed in the reaction vessel with the sample. But when you use nitric acid, what is it that we need to do? They're saying you also need to have a combination of hydrochloric acid hydrofluoric acid, as well as hydrogen peroxide may be added to this particular sample. Remember from the previous slide that we've had, we are saying we can use sulfuric acid and phosphoric acid at a temperature 280, pressure 40 psi. But when you just use hydrochloric acid, the temperature is, if you remember, the temperature was 420, lower. But now in here, if you use nitric acid, because nitric acid is likely to contribute the NO2, the NH2, those are ligands. The diamine, yeah, those the amine, those are strong ligands that are present in most of the complexes, like EDTA, ethylene diamine tetraacetic acid. You find that there is an amine ligand there. So because of the nitric acid, which is likely to bring the amine ligand, it's important that to prevent the complexing of the metal, instead of you digesting just that metal, you end up forming now a complex. Yeah, and once you form a complex, then you need advanced methods to separate those ligands to remove them from the central metal. So to prevent complexing, it's important that you add hydrochloric acid, you add hydrofluoric acid, or you can just add hydrogen peroxide. That is very, very important. Okay, so these are methods and how it's done and stuff like that. So I think that's where we can end for today. It's important. I'm going to give you a summary. It is important that when you're choosing the method to use, one, consider the composition of that element, because if that element is having a nitrate, not nitrate, rather a hydroxide, you find that if it's a group 2, hydroxides of group 2, or even carbonates of group 1 elements, they do not decompose. The metal carbonates that decompose are those for group 2, like calcium carbonate, they're able to decompose, not lithium carbonate. Yeah, so if you find that such samples cannot decompose by heating, then you don't go for dry ashing. It's important you go for wet ashing because of the presence of acids and as well as elevated temperature and pressures. You find that these samples become easier to dissolve. So that is what this microwave acid digestion is all about. It's all about weight digestion and how it's done. The times I like asking questions, why is it that nitric acid is not the best acid, despite being the strong acid? It's not the best choice for acid digestion. It is because it helps in the formation of complex metals. All right, so that's where we end for today. If you have questions, you can reach me on +26 0975578 694. All right, enjoy the rest of the day.